In the previous videos, we have done straight lines, the angle between the lines, all these things, correct? Now we'll move to the next part of the chapter. That is, we are going to consider plane. Now, whenever we talk about a plane, guys, imagine this one, that let's say you have x, y, and z axis. Okay, so something like this with the origin O. Now, a plane is basically collection of lines in one single direction. In the sense, suppose say this is one line. Above this, one more line, one more line, one more line, one more line. For example, you can say this one. See, this is one line, one more line, one more line. Now, collection of these lines, this basically is a plane. Correct? That means in the XYZ axis, that means in space, if we have to write a plane, so what we can write something like this. See here, see something like this. This becomes a plane. Or here you can write this A, B, C, D. Now here A, B, C, D is a plane. Okay, A, B, C, D becomes a plane. That means how exactly we define a plane? Because see, mathematically we can say that it is the collection of lines that is basically a plane. But whereas when we say collection of lines in another dimension, another axis, that basically is a plane. Now, mathematically, if we have to define a plane, we write it in terms of equation, right? Now, whenever we write anything related to space will have two forms of, for forming an equation or writing an equation. One is the vector form, one more is the Cartesian form. Now, what we are going to look at, first will start with the derivation of the equation of a plane, first in the vector form, then in the Cartesian form. Fair enough. So first start with the vector form now. Now, when we try to calculate the equation of a plane, there are certain criteria, or more like conditions, which the plane has to satisfy. We can't just randomly say, okay, what this is a plane, find the equation of the plane. No, it makes no sense. That means a plane, now it has to pass through a particular point, correct? Any point, some random point x, comma y, comma z. That means here what we'll do, we'll take the x, y, and z axis like this. Fine. Now, in this, let's assume that we have a plane, something like this. From the origin, what we'll do, we'll draw a normal. Say this point is normal, n. That means we can say that ON is the normal. Some normal. That means ON is perpendicular to the plane, isn't it? So if let's suppose say this is the plane, then this is going to be ON. This is perpendicular. Now, next point, what we'll do, we'll take some arbitrary point P. Okay, this point is P. Now, what we do, we join OP. That means here, point P, okay, point P is given by x, comma y, comma z. Say OP vector is equal to R, some vector R. Fair enough. Now, here, if you look at this one, ON is the perpendicular distance, correct? Like this perpendicular distance. Say mod of ON is also a vector, isn't it? Mod of ON, let's call it as D, where D is not equal to 0. Some number is there. That means vector ON becomes D into n cap. N cap is the unit vector, right? So D into n cap. Now here, suppose what if I join N and P like this? Look at this, O and P becomes a triangle, isn't it? Now, if you apply the triangle of addition, now what do we have? Triangle of addition, ON plus NP is equal to OP. Correct? ON plus NP is equal to OP. That means NP becomes OP minus ON. Now, what is a OP? Vector R, isn't it? What is ON? Minus D into N cap, isn't it? Vector R minus D into N cap. Now, this is basically vector NP. Make sense? So, let's call this as equation number 1. Now, NP is a vector on the plane, correct? And ON is a vector perpendicular to the plane. If these two vectors are perpendicular, then the value of dot product would be how much? 0. That means what we get now, or what logic we are going to use, is NP dot ON is equal to 0, isn't it? Now, in place of NP, use that equation 1. That means R minus D into N cap dot D into N cap is equal to 0. Now, D is not equal to 0. That means R minus D into N cap dot N cap. This should be equal to 0 because D can never be 0, isn't it? So, what do we get here? R dot N minus D is equal to 0. What is N cap dot N cap? 1. Like I cap dot I cap is 1, right? Like just like that. So finally, what do we get? We are going to get R dot N cap is equal to D. So this is the equation of a plane in vector form. R dot N cap is equal to D. This is the equation in the vector form. Now what if we do the same thing in the Cartesian form? The point P was what? P is equal to x comma y comma z, correct? Some arbitrary point. That means here you can also write this as xi plus yj plus zk, isn't it? Now, n cap is a vector and it has a direction cosine of say lmn. Okay, that means n cap has DCs. DCs, what are the DCs? lmn. Now, n cap, if you have to write in the vector form, n cap when you have to write it in the Cartesian form, this becomes n cap is equal to L into I cap plus M into J cap plus N into K cap. Correct? This is what it is. Now, what is the formula, whatever we just did? It is R dot N is equal to D. Correct? R dot N is equal to D. Now, if you substitute, what is vector R? Xi, because this is OP, right? OP is nothing but vector R. Xi plus Yj plus Zk dot Li plus Mj plus Nk is equal to D. If you multiply I and I, dot product, no? So what do we get? If you multiply, you will get Lx plus My plus Nz is equal to D. So this becomes the formula in the Cartesian form. And this is the formula in the vector form. This is the formula for Cartesian form. Fair enough? Now, these two, or this is the equation of a plane in both vector and Cartesian form. Now, the same thing can also be written as ax plus by plus cz is equal to d. That's also possible. Okay, that is also okay. That is also the case. But in general, we write in terms of DCs. That's all. Fair enough? So, this is the equation of a plane in both vector as well as Cartesian form.